Okay, 10 after. Can't really see exactly who's in the room and who isn't, whether it's all students on the course or whether there are other people, but just in case, I will mention that this is the fourth session of CS 394, which is a new course on virtual machines, and I'm the instructor. My name is Mario Walchko. I'm an architect at Oracle, so I'm kind of a visiting instructor. And today we have a little experiment, something I've been wanting to do for a long time, which is to talk about landmark papers with the authors of those papers in the room, so they can face the music and answer to what they did. I think this is going to be a really interesting experiment. It might be a little chaotic. We'll see how it goes. But the idea is you should have all read the paper. Many of you have and have submitted questions, which I have printouts of here. I'll give a little bit of an introduction to the background of the paper and one or two observations on it. And then we'll sort of set into the questions in the discussion and see where it leads us. This is particularly pleasant thing for me because this is kind of the first paper I read that really made me think very hard about virtual machines and virtual machine implementation right at the beginning of my career in virtual machines. And so I've been waiting to do this for 30 years. So without further ado, our guests are Peter Deutsch and Allan Schiffman. Peter is a legend in programming for the many, many implementation accomplishments he's had in a wide variety of languages, a wide variety of techniques. Was a legend even when we started this. Allan, I know much less well, but has obviously done some great stuff. We had a fun conversation over lunch as to the things he's been working on since this paper, which have not been in the field of language implementation. But they came together in some context, which I don't know, maybe they'll talk about, to do this work, and I think really kind of almost invented an industry around virtual machine implementation. And I claim in the abstract that most, possibly all, high-performance VMs today can trace their legacy back to this paper. So I think it's incredibly important. So cast your minds back to 1983. Looking around the room, I suspect there are not many people who have memories of 1983 in this room. But I had a look at the Wikipedia page for what happened in 1983 and pulled out some images which jarred my memory. So some random politicians, movies that I'm sure you'll recognize from the time, and TV shows. The space shuttle had been flying just a year, and it was the year in which the second one was launched for the first time. It's Challenger. And in computing, the Free Software Foundation started the GNU project in 1983. And the ARPANET finished its conversion to TCP/IP protocols. And Kilauea started a routing, which has been doing ever since. So 1983 was when the work done here was conceived of, but I think actually to understand it better we have to go back a little further. So 1969, which even I don't remember particularly well, was where I want to begin the story and talking a little bit about the concept that led to the Smalltalk implementation. In 1969, Allan Kay did a PhD thesis at the University of Utah called the Reactive Engine, in which he posited a future in which computers would be portable, people would use them for education and communication and all sorts of creativity. There are a couple of sketches here which I found, which I think are actually from either the thesis or a spin-off paper from the thesis, and had this incredible vision of how the future would look. Now, remember, in 1969, computers were the size of things that filled a good chunk of a room. They certainly weren't portable, and even when this paper was published in 1984, you couldn't buy a device that looked like that. That still took another 10 years to come along. So it was an incredibly visionary thing. And one of the things he spoke about was about how programming would be accomplished on these devices and what it would mean to be an end-user programmer, because that was the vision of the system, that kids could use and program the system. few years after that, Xerox PARC got going, and Allan Kay joined and was one of the creators of the Learning Research Group, gathered around a number of people to try and fulfill this vision, and a language was invented which was called Smalltalk. And the name was chosen to convey the idea of children using the language rather than it being for seasoned professionals. And they started developing a number of different versions. Different machines, different implementations. That era is captured really well in this book, which I recommend, Dealers of Lightning, which is a history of Xerox PARC, a good read. But I wanted to call out in particular the 1976 version of Smalltalk, which ran on a landmark computer of its era, which was called the Xerox Alto. The picture of the Alto on the left. This was what was known internally as the interim Dynabook. So the laptop that was in the first picture was called the Dynabook. And this was kind of how far they'd gotten onto reaching the hardware vision of that by 1976. So this is still quite a long ways from a portable machine, but it is at least a personal machine, and it's recognizably familiar to what we recognize as for personal machines these days: high resolution bitmap display, single user, fast network port, fast storage. The Smalltalk-76 system was well honed and ported onto that machine. Graphics, kind of bitmap graphics in many forms, got invented at that time. For example, the motion copy and paste that came from that era. A few years later, and the next machine in the succession of workstations at one of the next machines at Xerox came along, which is the Dorado, which was a much more powerful, bigger, faster version of the Alto. And that was also a vehicle for the then new Smalltalk-80 language. And in fact, Peter Deutsch, who's here, wrote, I believe, the microcode implementation of that, which is described in this paper, which is part of this book right here. We'll talk about the book in a moment. By then, the system was very well polished and refined. It was very fast and performant and considered to be a very highly productive environment for doing software development. Shortly after that, Xerox made the decision to release the system to the world, or at least announce the system to the world. 1981, a special issue of Byte contained many articles on the Smalltalk system as a kind of a public unveiling of it. And I have the issue here. This actually has a very sort of special place in my heart and history in that not in the summer of '81, I just finished my freshman year as an undergraduate, had built a computer in the summer, which is how you got computers when you were a student in 1981. You went out and bought a kit and a soldering iron and you got on with it. And was looking for some interesting literature to read that might contain programs that I could run. Back then, the way you got a program into a computer was you typed it in, because there was no distribution mechanism for microcomputers and sort of standards for distribution of software. So I was wandering through a retail store in the north of England looking for interesting reading material and saw this on a shelf and thought, well, that looks friendly. It's colourful and I've heard of Byte, it may be an interesting thing. So I bought this magazine. It's the first issue of Byte that I ever bought. It's the only one I ever kept. And it was, I've never taken LSD, but it was, it's what I imagine it's like. Reading something that's so far from your conception of what the current standard is that it really is mind-bending. And one of my favorite papers in the issue was this one by Peter, which was about building control structures in Smalltalk-80. And there were other really good articles. This is now available in scanned form online. There's a link to it in the bibliography. Another highly entertaining paper is Larry Tesla's on modes and user interfaces. So after the Byte issue, Xerox also produced several books describing the system in detail. Here are my copies of them from back then. They're known collectively as the colored books for obvious reasons. The blue book was the one that described the programming language in some detail, and also had a section on the virtual machine and what it did. And the way it did that was it provided an implementation of the virtual machine in Smalltalk. So by reading that, you could assuming you could figure out what Smalltalk did from the earlier sections of the book, you could figure out what the virtual machine was doing and how to implement it in a straightforward manner. And then the orange book described the programming environment and all the tools available in the environment. And then the green book was a collection of articles by implementers on their implementation experiences and studies of the system. Because one of the things that they did was that they commissioned or persuaded or cajoled, I'm not quite sure how, a number of other companies and institutions to do implementations of the virtual machine from the specification and report back on how it went, how well it performed, etc. And those reports are collected in the Green Book. My master's advisor visited PARC around this time, saw the system, thought it was great, and set up a project, which I was the lucky recipient of, to do an implementation from the book. And to accomplish that, you needed one more thing, which was a copy of the Smalltalk world, the virtual image that contained all of the objects in the system that would run on top of the virtual machine. And so they also released to the world for a nominal amount a tape. Back then, stuff was distributed to universities on tape. Individuals couldn't afford tape machines, but universities could. And along with the tape came a little manual describing what was on the tape. That's my copy from 1984. And my advisor said, why don't you go build an implementation of this and we'll get the tape and see if we can make it work. Well, it took me about 4 months to build the implementation. It took longer than that for the university to raise a check in US dollars and mail it to the States and get the tape back. So I basically was done and graduated by the time the tape arrived. I'd managed to persuade them that what I'd done was somehow plausible. Luckily, it was, because a week after the tape arrived, we had it working initially. And thanks. I can show you. This is that very implementation, which still runs. So this is the Smalltalk-80 System, the virtual image from 1983 or so, running on a C implementation of the virtual machine as described in this book, which is what I created as my master's thesis. And if we refresh the display, you see it redraws pretty quickly. It's quite usable. What you can't get from this is the fact that the first time I did that refresh display on a high-end workstation of its era, which probably cost in the region of $30,000, it took 40 minutes to paint that screen. So this, I actually measured it. This system runs 18,000 times faster on this Mac laptop than it did on that workstation. So the goal, then, was to make this run fast on the machines of its era. And back to the slides. So now we're back up to 1983. And here are some machines of the era. On the left is the IBM PCXT, which had come out that year, was the second version of the original IBM PC. 8088 processor, about 5 megahertz clock, typically an eighth to a half megabyte of memory. The Apple III is on the top right, which was the newest machine in the old Apple range that had come out earlier that year. That was not quite 2 megahertz, 8-bit machine. On the bottom right is the Lisa, which was the Apple's sort of groundbreaking but commercially unsuccessful machine of that year that was to be followed the following year by the Mac. That was running a 68,005 megahertz. But for the purposes of this talk, the one we want to focus on is this machine in the middle, which was the Sun 1 workstation, which was a 68,000 base machine running at 10 megahertz with between, according to Wikipedia at least, between a quarter and 2 megabytes of memory. I've never actually seen one of these machines other than in a museum because they were not made commercially available in the UK. One question I actually have for you guys is, tell us more about this machine and what was the motivation for doing a port of Smalltalk-80 to this specific machine?
Can I hand a minute?
Obviously, you should talk entirely about the hardware, but I'll tell you.
I'm going to give you the mic, so I'll just leave it here so that you can.
All right. So which
I
don't do hardware. Which one?
A little into the microphone.
So
I do.
Right. So as you may have gathered, Allan and I kind of divided up the work. Allan did basically all the hardware work and some of the software work. I did most of the software work with help from several people. And I can tell you why the Sun 1 interested me. When I saw the announcement of its specs, it was as I recall, the first mass market 32-bit microprocessor. And we'd been working before that with Intel 8086, 8088. And my instant reaction was, wow, this is the first machine that I think we can actually get to run Smalltalk at a reasonable speed. And so that's why I was so interested in it.
So something you have to know about Xerox PARC, where I wasn't working there, Peter of course was, is that along the lines that you were saying, if you wanted to have a computer at some point you had to build it. There were all sorts of rules inside of Xerox, so I understand you can clarify some of this, but when PARC first started, they wanted to have a computer made by the then Digital Equipment Corporation called the PDB-10. And since Xerox made its own computers at the time, their rule was that PARC could buy computers made by Xerox or no computers at all. So since the people at PARC wanted a PDB-10, they had to build one themselves. And so that's what they did. Similarly then, the machines at PARC, they were really remarkable things, and you showed pictures of the Alto and the Dorado, and so nowadays when you say it had a bitmap display and it had a mouse and it had a network connection, you have to understand that no other machines, remotely had any of these things, and they didn't basically for nearly a decade after the people at PARC used them routinely. And you really have to understand how staggering that is as a thought. The only people, people didn't even understand the concepts of that unless you visited PARC. And you saw them. Famously, by the way, Steve Jobs visited PARC and saw for the first time bitmap displays, mice, network connections, stuff like that, and decided, I want some of those things. Anyhow, so I heard about Smalltalk-80. I worked across the street at a semiconductor company at the time, their research lab, and I actually designed microprocessors for a living, but I was working in an AI lab. And I was interested in machines for the same reason that Peter was, although I was hanging out with a bunch of Lisp people. But I decided the Smalltalk was really cool, and so I called across the street, and I met Adele Goldberg. And I said, gee, could I be one of these 5 people like Tektronix and Apple and UC Berkeley and stuff like that to have these initial machine implementations? She says, no, the contest is closed, basically. So I said, no, don't say no. I'm sure I can do all kinds of cool things. And she basically had me talk to Peter. And Peter talked about one of his ambitions, which was to basically stop putting things on special purpose Xerox-built microcoded machines and put Smalltalk on a machine that was, not the Xerox style of doing things, everybody else's style of doing things. 68,000. And I basically opened my mouth and I said, I can do that. And so I built boards. There was a kid at Stanford, kid my age, Andy Messersheim, and he was building this thing called the Stanford University Network Workstation. And I knew that. I met him a couple of times. I went over there and I told him that I would help him build some of those machines if I could get a couple. And so he built 10 for Stanford and I built 10 for Fairchild, and I brought 2 of them to Xerox. And and I built them with a soldering iron. Right?
So did it look like that?
It looked actually substantially uglier. Peter, do you remember? I think you were there. I gave him a bare computer, a multibus crate. I gave him a bare multibus crate, and if you weren't careful, if you like, Peter knows more than he does about AC, electricity, than microphones, because there was like bare, AC connections on the back of the power supply and stuff like that. So it looked nowhere near that neat. But I did finally put some of that in a sheet metal box so that people at PARC, who really weren't that hardware savvy mostly, wouldn't electrocute themselves. And then we worked together for a while on blackboards and stuff like that. Got some initial stuff. Half of the assignment, we tried to divide up the work. Half of the things that Peter gave me to do when I went back to my lab, I would do on a 68,000 cross development system that I cobbled together. And with really halting work, and Peter basically decided, you guys know what a cross-development system is? They don't. A cross-development system is one where, you start out with a big computer, and then that's where the assembly, the linkers and loaders and stuff like that are made perhaps with an emulator, right? And then you use that big machine to do the compilation stuff, the program preparation steps, and then you download it into this other machine. That's the way I did it. And Peter did the same thing, except I started with other people's software for the 68,000, and Peter developed it all his own from scratch. And so his work, he did that, and I was using other people's software, and he still beat me to almost all of my assignments, and I'll hand you the microphone at that point.
I don't know that I have much to add to what Allan said. The cool thing that I did in developing the cross development environment was we had the Smalltalk browser, and we had this development environment already existing, written in Smalltalk. It was quite a nice environment in many ways, but the only language that you could develop under it was Smalltalk, right? So in the course of building development tools for 68,000 assembly language, one of the things I started doing, and this continued into my research, for some time after that, was to take the Smalltalk development environment and generalize it to multiple source languages and multiple target languages. And I don't remember how much of that ever got distributed. I don't even know whether any of it got published, and of course many other people have done similar things. But that was one of the fun parts of that project was just building the development tools.
Thank you. So, just to make it clear, you basically started with a bare machine.
Yeah, we started from bare, but basically from a pile of chips, and by that I mean integrated circuits, and no development software at all,
Right.
and bootstrapped our way from there.
Okay. So quite a few of the questions were of the nature of, the paper talks about code not being paged and other things which you think of normally as OS capabilities, and they weren't there because there was no OS.
Actually, it was Dan Ingalls, right, who had the famous phrase, I think, saying, I don't know, can people hear me, by the way, because I don't have the microphone, good. Dan Ingalls said, an operating system is all the things that you forgot to put into your programming language. And so the tenant, right, that was Dan, wasn't it?
Yeah. It may well have been Dan, and like many things that Dan said, it was very clever and it was very insightful and it wasn't entirely correct.
Right, exactly. But there was very much the style in at Xerox at the time to not fetishize operating systems at all. They were sort of a means to an end, and they weren't very important things. They were down there in the guts of the machine somewhere, and you basically didn't worry about them because they weren't very important. What was important is what the developer used, because PARC was just a place full of software developers. And so, yeah, insofar as there was an operating system, there was just a pile of device drivers at first, because we had a mouse and a keyboard and a display, and we had to write stuff for that. So you might have thought that's an operating system. It mostly wasn't. It was just primitives for all of these things. And then later, there was a network drive. First a serial port driver to download stuff into the machine, and later there was a network driver. Although I didn't do it, I think Mike Hagman did that. And then later there was a disk driver. So if you want to call that an operating system, a pile of drivers that the virtual machine could basically read a block from the disk, then it had an operating system. But I don't think it was anything that you guys would recognize as an operating system.
Just if I may add
Sure.
a little bit to that. A lot of the functions of an operating system have to do with basically with resource management, protection, scheduling, allocation of resources. Smalltalk was conceived really as a single user and for a very long time single-threaded language. And so many of the functions of an operating system simply were needed. And as Allan said, we added device drivers. But the higher level protocols, for example, for the network, were all implemented in Smalltalk. And if I'm not mistaken, at least the first disk file system was also implemented in Smalltalk.
Absolutely. Yeah.
And again, if you don't have to worry about resource allocation and protection, a lot of things become simpler.
Yeah, and that's why Dan was basically half right, namely that if you had a simple enough problem, then in fact,
Right.
Almost all those things. And although it admittedly it was single-threaded, there in fact was, of course, some mechanisms for scheduling that was at the language level for user visible multiple threads of control and so on. Again, these are very visible in the language, and by visible I mean that if the user didn't like the scheduler, they could change it.
Can you tell us a little bit about the architecture of the processor and the available resources you had? How much memory was there, for example, in the systems that you were using? Because the description of the machine that I found on Wikipedia has this fairly wide range of memory that you could plug in, and it seems like you'd need to max it out.
Yeah, that's what we did. It was, again, these are boards that basically I stuffed. Luckily, you probably didn't know this, but Fairchild was still in the memory business at that time, so for me, memory was free. Not memory boards, but memory chips. This is the era of, you're going to find this really, really hard to believe. 16 kilobit dynamic RAMs were the sort of thing of the day, and you could get larger things than that. Fairchild actually sold 64 kilobit dynamic RAM as well. So this is, and basically a 1 megabyte thing basically crowded up a whole board, right? That's 1 megabyte. So anyway, I'm not trying to sound like, and we lived in dog houses or whatever, but that's just really the way it was, right? And so there were multiple, so this was Andy Bescher's, it's a private memory bus of Andy Bescher's design, part of the Sun One. It had a private, it had very fast memory, unusual for the time. It was really an unusual, very economical design. Andy was really quite, I shouldn't speak in the past tense, he still designed stuff. Right, so there was 2 megabytes of memory. The machine clocked at about, I think the first boards clocked at 10, and the ones that we ultimately used for a while were clocked at 12. You got to understand there was no cache memory. There was nothing that you would recognize as modern computer architectural features that you worry about in the school, like pipelining, branch prediction, all this kind of stuff wasn't necessary because these machines basically didn't have these sorts of features. You don't need branch prediction if you don't have pipelines. You don't need cache invalidation techniques if you don't have a cache. The machine didn't have a memory management unit, although Andy had in fact done a memory mapper unit. I don't know if you guys know about this nomenclature, but basically there still is a purpose why you might want to dynamically map some of the bits. You want to be able to still have, even if you don't have virtual memory, you still might want to have flexibility about mapping the processor's address space to physical memory. It turns out to be convenient to do that for a bunch of reasons I won't go into. So there was that kind of stuff on the board. But in particular, the 68000 wasn't a virtualizable architecture. So what that means is, I don't know how many of you guys take like computer architecture courses, but instructions weren't interruptible. So you weren't, which modern machine, it's really would be hard to find a processor nowadays which doesn't have that. So in other words, you might take a page fault, namely in the middle of a memory reference, you say, well, that page isn't there, right, for a non-existent page, and you interrupt, you go to supervisor space, and then you pull it in from disk, all this kind of stuff, which you guys take quite for granted, the 68000 simply didn't have. So the issue of saying virtual memory, the Sun One, and until the 68020, which was like several years later, the 68020 was until the 68020. This architecture you couldn't do virtual memory, except in a very unusual way. If you want to find out the unusual way, you can Wikipedia Apollo Computer System, which did it's like amazing. They actually used it. What they do is they put one processor in suspended animation, boot up another processor, and have it pull the page in, and then resume the first processor. That was their trick. So until then, So you do know about that, right?
We have.
Cool. So anyway, a very by today's standards, amazingly primitive.
And as far as the instruction set architecture goes, there was nothing really startling about it. Machine had 16 central registers, partitioned actually into eight address registers, 8 data registers, more or less a 1.5 address architecture.
No floating point.
And no floating point in the 68,000, although there was a provision in the instruction space for it.
How many clocks to memory?
Yeah, that was an interesting point. Essentially, there was a wait state kind of architecture. What they normally expected was that memory couldn't keep up with. There was essentially an architecture where there were, at the minimum, there would be 2 clocks to do a bus fetch, right? But they didn't ever expect anybody to be able to build memory that'd be fast enough to do that. Although Andy Betchersheim, the designer, actually managed to do it by pulling a bunch of really weird tricks, one of which I suggested to him. So, but in practice, it took somewhere on the order of 10 clocks to have an instruction that referenced memory. It took something on the order of 10 clocks. So.
Okay, cool. So, let's go into a little bit about the paper and the implementation of Smalltalk. So I pulled out these 4 main contributions from the front of the paper. The first one, I think, is the one which is the sort of the standout of the 4, which is, I believe this is the first true just-in-time translator, in that it took Smalltalk bytecode, which is compiled ahead of time in the programming environment and sort of persists, and generated machine code on demand at the point at which that bytecode was needed to be executed, and cached the resulting machine instructions so that they could be reused later. We were having a conversation at lunch around this, and no one can think of a predecessor that had those characteristics, although there were systems that did some amount of dynamic compilation. For example, there was a terminal done by Bell Labs called the Blit, and Rob Pike did an implementation of a graphics primitive called BitBlit that generated machine code on the fly to run this primitive, but the machine code was then thrown away after each.
And it wasn't a general purpose.
Right, it was for one specific primitive, so it wasn't a general purpose compiler. And the other one you mentioned was the regular expression compiler.
Done by Ken Thompson 68, and it would just take regular expressions. It would generate the DFAs and convert the DFAs to machine code. It was pretty impressive, but again, not a general purpose programming language, and only done once and thrown away.
Can you say something about the structure of the compiler and the kinds of transformations it did, if any, or what the general organization was?
Oh, goodness. Well, so I'm going to preface this by saying, this all happened over 30 years ago. I'm almost 70. I'm not going to remember everything, and I'm going to get some of it wrong. Just deal with it. So the thing that made this task relatively simple was that the translator all just worked on one method at a time. That was all it had to do. The way the control got into the translator was a method lookup happened in various ways.
Everybody's hip to method, Smalltalk pilot method.
Okay.
Yeah. So a method lookup happened, and there might either be a cache miss or there'd be a cache hit, but what was in the cache had not yet been translated. So control would come into the translator and basically said here's a method, translate it. So the translator worked in a very, very straightforward way. It basically it had a little it had some internal bookkeeping that emulated the state of the runtime stack. It basically worked its way through the bytecode sequentially and generated code nearly bytecode by bytecode. Also, at the same time, building up a table of any literal object references needed by the code. That is, any literal object, including numbers, that was referenced from the bytecodes. That literal would also have to appear in a table to the side of the translated code. The one really significant optimization, and so it could have generated completely naive code. The bytecode is for a stack machine, and so the translator could have emulated the virtual machine stack in a native machine stack, you have a push local variable bytecode. Well, you pick up the local variable value and you push it into the runtime stack. The one optimization was that there was basically a one element cache for the top of the runtime stack in a dedicated machine register. So, for example, if you wrote A assign B, it didn't push A and then pop it into B. It just loaded A into the register and stored it. Let's see. What other interesting?
Well, deferred reference counting was probably.
Oh yeah, well,
was
so that really wasn't an optimization of the translator. It was an optimization of the whole system. The microcoded Smalltalk implementations all did reference counting, period. So that meant that every time you loaded a local variable, well, you were creating a new reference. You were copying the reference into the stack frame, so it had to increment the reference count. Whenever you stored a local variable, well, that reference went away, so you had to decrement the reference count. That isn't quite how it worked, but close enough. So Dan Bobber and I published this paper in 1976, which wasn't a bad idea. It hasn't turned out to have a whole lot of staying power. But the idea was, if you have a system in which computation is going on in the stack, rather than do reference count operations every time you load and store, change the value of a local variable, you only maintain reference counts for references from off-stack storage. What's the problem with this? Well, the problem is then you can have objects whose reference count is 0 because they're only referenced from the stack. So in order to deal with this, you have a table maintained at runtime called the zero count table of objects that have or might have 0 reference counts. And then the idea is that you periodically stop computation and you basically run the stack against the 0 count table. Anything that's in the 0 count table and not referenced from the stack you can reclaim. And we call this transaction reference counting because I thought of the epochs between instances of this operation being sort of like transactions in a database system, which in retrospect shows me that I didn't really understand transactions at the time. But so that was the idea, and so we used that approach in the translating Smalltalk system, so that the normal things that happen in the course of computation didn't require fussing around with reference counts, and that actually was necessary to make production of machine code really practical, really feasible.
I mean, you can see what the consequences of not doing that is, right? Because basically what ordinarily would be, ignoring the register copying optimization, would ordinarily just be a memory store with an auto-incrementing register. That's how the 68,000 accomplished stack pushes. Would become something much more complicated, where you have to do a dereference, an indirect reference to some object table thing where the reference counts are kept and things has to be incremented and possibly tested to make sure they don't overflow and stuff like that. So you can't imagine a simpler operation than simply pushing something onto a stack, right? Each one of those stack pushes or pops would be like 5 instructions, right? So that's a pretty significant thing to optimize, even if you had this cost in the end where every so often you have to wake up and you have to run a couple of hundred instructions to fix up something. Turning something that might be one instruction, not turning one instruction into 5 is pretty significant.
And so perhaps when we get further down the list, I can say a little more about some of the trade-offs involved in this deferred reference counting thing.
One question I had was, the paper calls this out as one of the sort of the 4 features at the front. Was this the first implementation that you had done in a kind of a production system of this technique, or had it been used in earlier systems?
That's a good question.
Because that's, this is 7 years after the original paper. And if that's the case, what motivated the original paper?
I don't recall. We at PARC didn't do any implementation of deferred reference counting. I don't know whether anyone else used the technique. What motivated the paper was a bunch of benchmarking and profiling that had been done on the microcoded implementations of Smalltalk-76, and we discovered that reference counting overhead was, very, very substantial. But to the best of my recollection, we didn't actually go back and change the Smalltalk-76 microcode.
So you came up with this idea, wrote a description of it, and then kind of kept it in your back pocket until the time was right to apply it.
It does seem a little implausible, doesn't it? But that's
Well, it's actually not as good to do it in microcode, actually, because when you do it in microcode, there's still, in fact, there's a substantial overhead, microcode overhead, because you have to keep a table of the stack state to know when, in fact, there's been a transition, right? So, in other words, you don't really have this additional step, the sort of a compile time step, as it were. When in microcode, you basically only get to look at one instruction at a time. Right?
Well,
you have to keep a table. You have to sort of memoize what's going on. It's not so,
no, but, I mean, we could have redone the Dorado.
Oh, I see. Right.
The
You could
Dorado
have,
bytecode interpreter.
you could have done bytecode to bytecode translation or something like that.
Well, no, we wouldn't even have had to do that because I mean the push and pop bytecodes were their own bytecodes, and we just could have written the microcode in a way that just didn't do reference counting, and then every so often or whatever it probably would have fallen out to macrocode to do the reconciliation. So that's what my memory is telling me happened.
Okay. So tell us about the language that the system was written in and how you dealt with that.
So the system that was described in the 1984 POPL paper was written in Motorola 68000 assembler. And
How much assembler?
I was thinking about that as I was driving here, and I don't honestly remember.
My favorite unit of measurement for
My guess is
was inches of listing.
my guess is that it was perhaps tens of thousands of instructions.
And actually I do remember inches of listings, though, because do you remember it was printed in one of those? Remember the Xerox books where you perfect bound? You do know that? I mean,
Yeah.
I mean, it might have been Russ Pinson or somebody had done that, right? And I had one, and it was like that thick. So
Right. So that's probably
10,000 lines.
that might be 150.
yeah, I think it might
150
be.
pages.
It's some tens of
So
thousands.
yeah,
It's hard.
low tens of thousands of machine instructions.
Yeah.
I don't remember how many comments it had.
But was the motivation to use assembly simply that you had no better tools and you didn't want to port them, or were you trying to deliberately squeeze every
It
last
never
cycle?
would have occurred to us to do it in a different language.
Well, no, actually, it did occur to me to do it in C, and I looked around at what was available, and I said, the language, the compilers, they're not stable enough.
Mhm.
They're probably not going to generate very good code.
I actually remember having a conversation. Yeah, okay, so we're talking about the same thing, but it occurred to us, it seemed to me that perhaps we had a discussion that lasted all of 10 minutes, right? So I talked about the runtime, because you may or may not recall, I had like Steve Johnson's C compiler for the 68000.
Right.
I had all this stuff.
Right.
I knew what the code was generating. I showed it to you.
Right.
This conversation did not take very long.
Right.
We were going from, it would have really been a disaster.
It would have. Yeah, that's right.
No, the system got rewritten in C.
Yes, I know, but that was
later.
a different era.
Right. Different. Many things were different, and we can talk.
And really, it was almost 10 years later. No, 7 years later, right? Because really, this work honestly started in '82. You say the paper was written in '84,
Well,
but the
published
work
in 84.
it was published in
I think it was
'84. It
a
was written in
January
'83.
84 conference.
And so when we took another run of the problem, it was like nearly 1988, right? So from
87.
yeah, I guess late '87, right? So going from '82, right? It's 5 years, right? So there's a lot of compilation technology under the dam at that point. So and also we were constantly into microcode. We had something to beat, right? Nobody at PARC. I thought this was doable because I was a micro designer, but everybody at PARC thought this was tilting at windmills, right? This was a pointless exercise. It was impossible.
And so our goal, or at least
it was a joint goal we had.
One of our goals was to beat the Dorado microcoded implementation performance.
It was pretty. It was, yeah, because there were a lot of naysayers, right? And Xerox really had internally at PARC, they really thought that microcoded implementations of these bytecoded virtual machines was the only way to go, and basically doing other things was crazy. And there were commercial companies that believed the same thing. I'm thinking of the list machine companies, for example. Right. But lots of people said that's the only way to build and affect the future of such machines. You got to realize that, and this, I think, one influence of the paper, which you may or may not agree, but I think that our paper actually resonated into the risk work that was here. Because people might have said, well, risk work is ridiculous, and anything architectures are going to have to get more complicated. Because instead of just having C-like languages, we're going to have super cool, whizzy-bangy languages like Lisp and Smalltalk, and they'll be really important. And simpler machines won't work, it'll be more complicated machines. And, Berkeley professors like Patterson and, students like Unger, took our thing as an inspiration, I think. I mean, maybe I'm looking at it from too much of a Smalltalk perspective, but I think that had a big influence, and they had a way to shut down the SOAR project here. Totally anticipated that by saying, no, you could. This is a simple machine, but you can implement Smalltalk on it perfectly well.
Smalltalk, just as an amusing side note, Smalltalk's integer arithmetic was the motivation for the attack integer instructions on the Spark, which in retrospect
implemented
were not a great idea.
No disagreements there. Okay, so the second listed contribution is the on-demand conversion of context or activation records from on-stack to hybrid and then heap allocated forms. Something which I think I had to read the paper many, many times originally to understand the mechanism of what was going on, and perhaps hasn't had as wide impact as it might have, simply because languages that I can't think of any of the languages that require this in any serious sense. But clearly an important technique to gaining performance in Smalltalk.
Well, I think that would be the cleverest thing in the paper. It was the inspiration for was it Dan Ingalls who said the implementer must cheat but not get caught?
Yes, it was Dan.
So one of the remarkable things about the Smalltalk-80 system was that it has complete reflectivity for its execution state. So what you would think of as stack frames, not only byte compiled code, but stack frames are defined as objects in detail in the system. In the system description.
And the system made use of that.
And the system made use of it. I mean, the debugger was written entirely in Smalltalk, and it did all the things that it did by manipulating, manipulating these context objects.
And then people made cool distributed Smalltalk systems where they would package up existing running objects and ship them over the network to let it. You have a subroutine in mid-execution. You ship it over to another machine to have it execute, and you wrote that description in Smalltalk. Right.
And so to make all of this possible, as I said, there were specifications for the execution state. Well, one of the big challenges in doing translated code was to maintain, complete faithfulness to that aspect of the system description. And in order to do that, we needed to come up with a way such that when a context, Smalltalk terminology, it's what everyone else calls a stack frame, when a context was actually being used for execution, it would be sitting there actually on the machine stack, and its format would be governed by whatever it was that made execution work best. But when you looked at it as an object, it had to be an object, and in particular, what that meant was that execution contexts had to, at least in principle, had to behave when necessary as being heap allocated rather than stack allocated. I don't think I want to try and take the time even to summarize how we went about making this work, because it was kind of complicated and tricky, and I think the paper describes it. The basic idea was that when a context was created, it was created for execution. And so the issue was, so there were two issues, namely, what happens when someone tries to reference a context as an object? And then, what happens when a context that has been referenced as an object is needed for execution again? So when a context is needed as an object, basically what happened is that that context and that context, an operation called stabilization occurred. So the context was copied into an object, and it was probably on an execution stack somewhere. So the return address in the frame that would return into that one was changed to a trampoline. So that when you were going to return into that context, the context was hauled back from the heap and put back onto the stack. And
You want to explain what a trampoline is? Does anyone know what a trampoline is?
oh, come on, they've got it. So that's kind of the 30-second summary. And it was a little tricky to make it all work, but it really worked. And it wasn't very fast, but it hardly ever happened. Yeah, so we had to do it, and so that's more or less how we did it.
It's really hard to understand, even in modern, even in languages that came well after Smalltalk. This idea that you could refer, they had reified execution states. This is a very, very strange one. In Smalltalk, there's a pseudo variable called this context, and that's basically the way that you get a handle on it. But imagine if you're a C programmer that there was a variable called register 1, and any time that you wanted to, you could take a peek at register 1 and assign it to the variable A. Right? Imagine you could do that. Because the machine dynamic state is part of the language definition. And that's really a very, very strange idea for people coming from ordinary languages, but then it made it unnecessary to write system code in languages outside of Smalltalk. I mean, that's the trick, essentially.
So this whole idea that you can sort of step back and look at your own execution context as objects, that idea generically is called reflection, and there's a massive thesis on the subject of reflection. It's Lisp oriented, but it has a lot of ideas in it by Brian Cantwell Smith. I don't remember the title of the thesis, but it's sort of the big thesis on reflection.
Interestingly, I think most of the languages that have provided some kind of reflexive capability still haven't gone all the way of giving you full introspection on stack frames, or sometimes they've allowed you to look at stack frames without modifying them. I'm thinking of Self and Java have some capabilities.
Right, and often what people mean by reflection is being able to look at the class, or for an object-oriented language, to be able to examine the class structure, right? And that's considered to be a big deal.
Reflection has, and I didn't realize this until many years later, reflection has security consequences. And that may be one of the reasons why people haven't pursued it, even though it greatly simplifies some of the programming tools.
So the other one contribution I'll mention, because we've already talked a little bit about deferred reference counting, is the inline caching of message send targets. And the paper describes, I think, the technique in good comprehensible detail and the motivation for it. One question I had was, what triggered the observation of the behavior of message send? Where did that come from? The thought that, maybe the type is constant and we can exploit that.
I don't remember. It wasn't me. Allan says he thinks it was Butler Lamson.
Maybe this is a reconstruction of something. I seem to remember something along the lines of us writing send sequences on the board with checks, the usual hard work of checking to see what the class is, and is it, do you have a one-word cache followed by a larger cache of and things like that. And Butler, looking at the code that we wrote very cursorily, and he said, well, the silly thing is it's probably the same damn type every time around the loop. And then walks out of the room. In disgust, basically.
Right.
So you guys are wasting your time, because Butler really wasn't a fan of dynamic polymorphism, was he? Right? So that's the way I remember it. But as you say, it's 35 years ago. So who knows?
I do know, however, that the original idea of doing dynamic translation was also Butler's idea. When I said that I was thinking of doing compilation on the 68,000, but I said that I was very concerned about the code size. You know, this is just a casual conversation in the corridor. Butler said, "Well, you know, why don't you just cache the compiled code?"
That should have been an acknowledgement in the paper, surely.
It probably should have, yes. But Butler's famous for so many other
Yeah,
things.
exactly. He doesn't deserve more credit than he really has.
Okay. So in looking through the paper, I found a few other things which I think have had some lasting impact. And I've certainly been used in other systems. So one is the idea that you only get to look at state at certain well-defined places, and so you only need to maintain the reverse mapping from machine state to abstract state only in well-defined places. And that's been an enormous hammer that's been applied in many systems since then. I don't know if there's anything you want to comment on that.
Oh,
that
only
technique.
that you know, the fact that those are the only places that you can see the state was almost, as I recall, that was almost a side effect of the fact that we had to make some decisions about where you could do thread switching, and we decided that the only places that you should be able to do thread switching were basically at calls and backward branches, and so, you know, once we had that, then the mapping tables that we had to tack onto translated methods.
You do remember we almost didn't do any of this, right? Because we said, wait, you're going to need a table that's going to map every instruction, right? Every native code instruction to every decode instruction, right? That was the first thing. And then we said, oh, wait, no, we won't.
Right.
Right? I mean, it lasted like a minute. Said, we can't do this at all. It's crazy, right? And then you said,
No, actually,
wait.
I didn't remember that.
Yeah. Then you said, wait, it's not crazy.
Right.
What did you have to do in terms of the interrupt handler to make sure that this invariant was maintained? Because presumably you could take an interrupt from the keyboard or the mouse or some external device.
But that was all handled at the device driver level.
Okay.
You couldn't interrupt a Smalltalk thread at an arbitrary place. What we actually did, and Alan, you're going to correct me if I'm wrong, please. What we actually did was the following. On the 68,000, one of the machine registers was dedicated for the stack limit.
Yeah, that's right. Yeah.
And so part of the
Oh, I remember that. I can't believe you remembered that. You've been smashing the stack limit.
and so
You remembered that. I didn't remember that until you started talking. Boy, what a hack.
but it was a good hack, Alan.
It was
so
a great hack.
So let me finish
Oh, I'm
this.
sorry, I
Let
stole
me
your
finish
thunder.
this
That
part.
was a great idea.
So we dedicated. So because, you know, it wasn't a page system, and we wanted to have very clean. You know, we wanted to have a very clean handling of running. You know, of being about to exceed the stack allocation. So as part of the preamble for every translated method, there was a simple 2-instruction sequence that compared the stack pointer against the stack limit that was held in a dedicated machine register. We had enough registers that, you know, that we could do that. And if we were about to exceed the stack space, you know, we went off to some out-of-line code. So and the stack grew down. So any interrupt that might result in a Smalltalk context switch smashed that limit register and set it at the top
So
of memory.
any call exceeds the stack limit.
Any call would exceed the stack limit. So you would go out to the context switch code at the next call.
That must have been your idea. I never would have thought of
I think that was my idea.
that. It's so wrong.
Did you do anything special at backward branches?
Let me think. You know,
No, the same check would have survived.
I think we made the same check at backward branches.
You just planted the check in the code.
Except there, what we did was we checked the stack limit register against the distinguished value that said an interrupt was wanted.
Okay. So in effect, it was a kind of
It was a flag. In backward branches, it was a flag, and it was just a flag check. In method calls, it's a combination stack limit check and flag check, which is amusing. That if one instruction doesn't work with two, right? One comparison doesn't work with two.
Cool. So
intercepting the return. I'd seen that. I'm trying to remember where I'd seen that before. I had used that before in other systems too. So
Yeah,
it's not that
I'm
weird.
sure it's one of
Okay.
those things that's been invented, 16
Okay.
times.
Okay.
Right, and we used it in more than one place.
So we used it. We used it actually for two things that I can remember. One was to detect returns into context that had been turned into objects. The other was that because the allocated space for the linear stack was fixed.
segmented.
Mhm.
In PS, it wasn't segmented. There
Oh,
there
in all the
only one
HPS.
segment.
I
Right.
remember HPS a hell of a lot better.
Right.
I remember. Yeah.
So when we were about to overflow the stack, what we would do is we would take some initial segment of the stack and just stabilize it. We have the machinery already,
Oh, I see.
and then
Okay.
I think we'd move the rest of the stack up, or maybe we'd stabilize the whole stack. I don't
Okay.
remember.
Okay.
And then the return address in the root frame of the stack would go off to say, oh, you've got to go and re-volatilize these contexts. So we use that basically for those two things.
Okay. Okay. Number two on this is sort of a similar trick, which is making fake objects with sort of stubbed out classes that only intercept messages and trigger things.
Right. The reason that we had to have those objects was that once you think for a moment.
You referred to this context, stuff it into some old
Right.
object. Somebody could go get
There were
it.
cases where you might be holding a reference to a context object, and nevertheless you needed to be able to execute in that object.
Right.
And so in both PS and HPS, objects were all referenced indirectly. And so there was this funny state of context where they had an object allocated, but their real data was still on the hardware stack.
Mhm.
And I don't remember the details, they're in the paper.
The paper mentions that there was a class provided for these fake objects called dummy context that provided some.
That's right.
Did
but
that, if you
it was not-
reflected on the
it-
system,
it was
could
not-
you
no,
could you
it was
see
not. No, it was not visible at the system level.
Okay.
No, the reason why you do that is because you have a debugger and you have to have some class for it, because the debugger, you could actually sit there and you'd see something in the frame and you didn't want somebody to look at it and see something weird.
But if I recall correctly, at the Smalltalk level, you never saw the
You
dummy
never saw
context
dummy-
class.
Oh.
That any attempt to actually
I
touch
guess
the
that's
object in any way, even
Triggered
to
the
ask
conversion.
its
Even to ask its class.
even to ask its class.
That I didn't remember, really,
Um,
because that wasn't really necessary.
I think there wasn't actually a dummy context class. I think there was distinguished
Okay.
value.
Well, I suppose so. Yeah.
So the hardest part is always double equals with the fake thing on the right hand side of the double equals.
Well, except that because we had
So this is
this
this way of comparing object identities.
right, but because we had this indirection table, the
Okay.
double equals check was the check on the address of the slot in the indirection table.
And then hiding representation changes by having the compiler emit compensating code. So if you had an actual method on contexts, it says in the paper you compiled a special version of it. And I read that paragraph just yesterday and I've already forgotten it.
Do the paper handy? Okay.
Yeah, right. We'll move on.
Okay.
All right.
Yeah,
We'll come
I'm
back.
curious. I don't remember that.
It rings a faint bell, but I don't remember what it was that we had to do.
So before we go to the questions, there was just one last slide, which is influences on the work. So there are a number of things referenced in the paper, and a couple of things that aren't. And I wondered to what extent these have influenced the design of the system, and versus being references that were found while the paper was being written. So there's Jim Mitchell's 1971 PhD thesis in which he describes the idea of, see if I get this right, deriving a compiler from an interpreter, I think.
Right.
Basically
And-
by expanding the routines of the interpreter.
Right. And I was tremendously impressed by that thesis. I think it's one of the great CS PhD theses. It was not, as far as I can recall, it was not, kind of in the front of my mind when I was doing the Smalltalk implementation.
Then there were the precursor byte-coded machines and threaded machines, BCPL, Pascal, Forth, and Lisp. Any particular
not really relevant. I mean, they probably were, had a strong influence on the choice to use bytecode as a Smalltalk implementation.
It was certainly at the time, the P machine had whatever you call it, commercial. It was certainly state of the market. Lots of people use Pascal, and so P machine implementation is very, very common. And there certainly were people who said that you might translate. As a matter of practice, people just had P machine interpreters.
Right.
But there could have been something in the air where you said, well, why don't you translate that to machine code and throw the P code away?
Right.
I certainly talked to people who would talk about doing that stuff.
Okay.
But that's not the same thing, really, dynamic translation.
Right.
That's kind of using P code as an intermediate representation to generate code, and that's what's in the executable file. That's not done at runtime necessarily.
And then the last thing was the work on APL done in the early 70s and late 70s on kind of on-demand dynamic conversion and representation. I'm not sure I would call it compilation, but there were some interesting tricks proposed in the work.
I don't remember that particularly as being influenced, but I mean, that talked about a change of data representation, right?
I think Phil Abrams' thesis does talk about compilation in response to interactive.
Sorry, that does not ring a bell.
But I don't know whether it was a thing that was actually implemented. Okay, so we have a bunch of questions that came in via email, so we can go through those and then open it up to the floor if we haven't exhausted everybody by then. So I'll take these in no particular order. Let's see. So Patrick, you asked about assembly programming. So are there any additional software engineering techniques available for dealing with such large code bases using a low-level error-prone language? Do any of these techniques translate over when managing modern software projects, or are they obviated by high-level languages?
In 1981, I was still capable of fully mastering several tens of thousands of lines of assembly code in my head and remembering all the details. And by today's standards, 10 or 20,000, 20 or 30,000 lines of assembly code is not a large project. So I guess I don't think that question is entirely relevant.
So there was a question about a discrepancy in the paper. There was a performance prediction made which was not understood at the point that the paper was written. Was there a subsequent insight as to where the discrepancy arose between the
You mean why we didn't get as much speed up as we'd hoped
yeah,
we'd get?
basically. It says hand analysis was performed and estimated the performance improvement due to inline caching, which suggested 20%, but there was a discrepancy and it turned out to not be as much as that.
I don't remember being particularly puzzled by it, though. I just sort of shrugged, saying, what you get, being off by a factor of 2 and then back of the envelope kind of thing isn't so bad. I guess we commented in the paper, and so it makes it sound. I guess I remember feeling faintly embarrassed that don't you remember that we thought that inline caching would pay off a lot more.
Mm-hmm.
So I guess that's why we mentioned it. And maybe if we'd known that it was going to be under 10%, maybe we wouldn't have done it. I don't know.
And I'm speculating that hand analysis was basically writing out machine code and counting cycles.
Yeah, something very much like that.
Let's see, the section on different contexts.
But one of the things that, when you think about that, that's not enough because you have to know what the ratio of sends are to total.
Yeah,
I mean,
right. You have to weight them with
there's a lot of coefficients different. I mean,
Right.
that kind of analysis would be correct.
Right.
That wouldn't be the thing that'd be wrong.
Yes, yes.
I mean, you might be off by a cycle or two because you generated slightly different code than you originally planned. But the thing that you could be really wrong about is, in fact, what the mix was by the benchmarks you ran and stuff like that. You could be off by quite a lot. So I think that was a good enough reason.
The section on different context representations mentions that the context starts in volatile mode and is converted to hybrid mode when it's thus referenced. Will the context be returned to volatile mode if the reference to it is lost, or is this such a rare occurrence it's not worth implementing?
I don't think that Okay, I have to sort of reconstruct what that means. Certainly, what happens is a reference to a context that was, that was reified. It can resume execution later. That's the whole point. And
Actually,
so
I have a better answer.
okay.
So, so you should think in terms of kind of a two-state transitions, from volatile to hybrid, and then from hybrid to stable, and from stable back to hybrid. So when a context goes from volatile to hybrid, an object is allocated, an object ID is allocated basically, but when a context is in hybrid form, the state of the context is still on the stack. So a context that can then go from hybrid to stable, in which case its state is transferred, and then it can go back from stable to hybrid, in which case the object reference still exists, but all the state of the context is on the stack. So a hybrid context is an object, all right, but it's and it's managed with deferred reference counting just like any other object. So if that object is ever freed, then yes, indeed, there's no reason why the context should have any machinery in it for being converted to object form. What I don't remember is whether hybrid contexts. I think hybrid contexts did have something special in their return slot, so that their state would get poured into the object
Yes, that's right.
when they returned. And if a hybrid context was free, I think we had to do something about that return address, and I don't remember what it was.
Well, why would it be free, Peter? You do a stack scan, and surely there's a reference to the hybrid context from the stack frame.
No, but what I'm saying is, if a context became hybrid because somebody did this context or whatever, and then
there's no further references.
And then that reference, just got dropped on the floor, so that there weren't actually no longer any actual references to the hybrid context. Right. Then at some point a deferred reference counting sweep would free the hybrid object, the hybrid context object, right?
But there's a pointer from the stack to the hybrid context.
So what you're saying is that from the stack
and then
frame,
when you're trying to do the hybrid, when you're doing the reference counting sweep, you're looking at the stack to see and why would you count that? I mean, it's essentially the equivalent of being on the zero count queue.
Right. So for hybrid context, there was in fact a reference to the hybrid context from the stack frame, and once the stack frame returned, then
it could be free.
Then it became a stable context,
because really, in fact, the hybrid context by definition was in fact there, because it would be perfectly free to say this context again in the running code. So and it would have to refer to the same damn hybrid context you had before. So in fact, it can't be free while it's still on the stack.
Okay, I'm going to pause. One more question, then we'll take a break. Object table. You had an object table.
We did.
And you maintain the object table even as the system evolved later on, despite the fact that generation scavenging came out and people found alternate representation, direct pointer representation.
Did HPS have an object table?
So why keep it?
Well, the reason that we had the object table in PS in the original 68K implementation was, number one, all previous implementations had it.
That's the best reason.
Right, and it just made some things simpler.
And you know what they were, right? So there's an inside thing in Smalltalk about switching the identities of objects, and people every so often would use them, and benchmark that used that. That's called become, by the way. It's a code word in Smalltalk for swapping the identities of two objects. And if you don't have an object table, typically the performance of a benchmark that does that thing would fall completely off a cliff. I mean, talking about order of magnitude, orders of magnitude inferior performance. And our benchmarks, in fact, did have becomes in it.
So, and as far as generation scavenging goes, I have to confess that I feel a little bit about scavenging the way that Einstein felt about quantum physics. works. I know that there are lots of reasons why it's a good idea, and it always makes me feel a little queasy. But in fact, HPS, the retargetable implementation that we did later on in C, did use generation scavenging, and I don't.
It used everything, Peter.
Well,
it had the most postmodern Baroque memory management system.
is that right?
Yes, I mean, of course, it had a classical garbage collector, but it was an incremental garbage collector that was guaranteed to always make forward progress. Yada yada yada. You know? I mean, it was like this whole hyper modern Baroque.
Right,
there were papers on it. They were very proud of it.
Right.
So much for the Einstein thing. I mean, you had
right.
all this. There were all these other guys
I know,
who came after you, and they did lots of good work.
And
among them were David Unger, by the way, who worked. He and Frank Jackson spent years of their life working on HPS storage management.
So the best answer is that's the way we did it before, and it was simple.
Okay. So I think we should take a little pause now. People who are not in the class maybe want to escape, and just might want a bathroom break, and we'll resume in 10 minutes.
One of the things to remember is whether or not the subsequent Cincom.
If anybody has any remaining questions, and, should be done with this section fairly soon, I think. So, so one question is basically, at the time, the battle between special purpose hardware and general purpose hardware was still open. In some ways, this was a victory in the war for commodity hardware. But is there a fundamental reason why commodity hardware, general purpose hardware, has won over the special purpose hardware that preceded it?
Allan and I both have answers, and Allan's answer is better, so I'd like him to answer it.
Okay. Well, assuming that you mean by special purpose hardware,
Language specific.
Yeah, language specific hardware. You'd think that it's sort of axiomatic that a processor that's built to only work on particular languages is of less general applicability than a processor that's built to work with every sort of language. And generally, a higher volume processor with more general purpose application will have more and better solid-state physicists working on the semiconductor processes that lead to, this is called learning curve economics in the semiconductor business. So basically what happens is more popular processors get built on more expensive semiconductor product lines, which have smaller geometries and better speed power products, and so they're on faster processors. So even if there's some theoretical advantage to making some cool architecture, if it's got one small fraction of it,
volume economics.
yeah, but it's volume economics. That's what counts the most.
And I have a different answer, which I think also has some validity to it. The reason that people think of they want specialized hardware for languages is because the elementary operations of those languages are in some way more complex than the ones provided by lowest common denominator hardware. They might have type checking or reference counting or goodness knows what. So they say, well, you do it in hardware. Well, so if you step back, what you see is that when you execute a program written in a language like that, each of those elementary operations involves extra work. So you're effectively doing something that's sort of like interpretation on an operation by operation basis. Now, the magic of compilation as opposed to interpretation is that basically you can step back and look at something more than the individual operation that you're executing at any given moment. And so you can float things like type checks, and you can float executional overhead out of the context in which it appears. So, for example, if you have a language in which the elementary arithmetic operations work equally on tagged integers and tagged floating point and general objects and whatnot, well, if you're executing those operations in special purpose hardware, those checks have to occur at every operation. Whereas if you can step back and look at a piece of code and say, man, this thing's doing a matrix multiply,
I only have to check the inputs once, and then I can just go ahead and do floating point. That's the stroke of genius in Jim Mitchell's thesis. And so I have an aphorism for that, which is compilation beats interpretation, and it's because you can take things that might have to be done at an atomic level, and you can float them out and have the operations that are actually doing work execute with much lower overhead on simpler hardware.
Right, and then hence the aphorisms that are more concrete. Never put off into runtime what you can do at compile time, or which you could also say never do inside the loop what you could hoist at the beginning of the loop, and so on and so forth. Yeah, and so that's exactly the steps that complicated hardware tries to save from the poor compiler developer who doesn't want to be saved because he's got a very expensive Berkeley education teaching him how to do exactly all those cool things.
Seems that memory constraints were an important motivation for all of this system. If memory had been cheap and plentiful at the time, how do you think things would have been done differently?
I'm going to give a slightly snarky answer, which is we would have run bigger and more complicated problems. But actually, you know, memory constraints come back in a different form. If you have, if you have an enormous amount of RAM, yes, indeed, there are many things that you don't have to worry about. But one's used to thinking, well, if you only have a limited amount of RAM, then your system performance is going to basically have its ceiling imposed by the necessity of swapping stuff in and out of the RAM to disk or SSD or something. And so you have lots of RAM and that problem goes away, but it comes back again. Because now you have the level 1 and the level 2 cache. And the system is going to, and programs are going to execute more efficiently if they're executing out of the cache, the instructions or the data. And people who write really high performance numeric and graphics and database codes actually have to worry about that. They have to worry about the cache size. So I don't know. The paper may allude to this, but it would be interesting to ask the question, okay, which way do you get better performance out of a system? Do you compile everything and then just let the code come out of RAM into the cache? Or are you better off doing dynamic translation and limiting the amount of code that you have in the code buffer, in the code cache, to some substantial fraction of the size of the hardware cache? I don't know the answer.
That's a good answer. But one of the things that people forget about, and Gene Amdahl was the one who. Gene Amdahl is a computer architect who was heavily involved in the creation of one of the most successful architectures of all time, the IBM 360 series. And he had a phrase called the balanced computer architecture. And his point was there isn't much point to having more memory than, say, now this is a rule of thumb he had at the time. There wasn't much point for a computer to have more memory than it could set to 0 in 1 second. So, and if you think about it, that might not be the right constant. But, how about a computer that had so much memory that it would take it 100 hours to clear, right? So you really have to ask yourself, what's the use of all that memory if, as a matter of practice, loading programs into that memory or whatever just takes too long? So there's always that speed-space trade-off actually extends quite some distance. And so, yes, you can imagine, what if you had 2 times as much memory or something like that? Some things become easier. But it's very unlikely with the processor technology at the time that it would have been all that useful to have memory that was 100 times bigger.
Do you think you could adapt the inline caching technique to a system with read-only code pages?
Yes, of course.
We nearly had to do that, actually, right? Because of we had the caching validation problem. We talked about
So what was described in the 84 paper was our implementation of the 68,000. We actually did a second implementation later, starting in 1987, 88, in C, that was designed to be instruction set retargetable. And we actually wrote code generators for, I believe, 6 different ISAs. And some of those ISAs required executing instructions to invalidate conflicts between the instruction and data caches. And I don't remember whether we actually did this, but I certainly remember thinking about it. On those architectures, rather than putting the cache inline in the instruction stream, what was put inline in the instruction stream was a pointer to an allocated cell off in data memory. And that basically solved the problem.
Yeah, but basically it's just an indirection. I mean,
Right.
It's not that horrible.
Right. So the short answer is any place, in the very few places where we did overriding in the instruction stream, we just replaced that with with a level of indirection up to something in the data space.
Right. Right. This thing about the cache invalidation weighed very heavily on our minds at the time, because even if the machine had an instruction for that, in some cases that was a supervisor mode instruction and simply not available to. So this is a very real prospect that we couldn't write to code space at all in some architectures. Although I don't actually recall whether we targeted any machines who actually had
Well,
that
except
problem.
of course to make runtime code generation work at all, we had to be able to execute out of some writable memory.
Some writable memory.
But I mean, I'm having some dim memory that on machines where you had to do a supervisor call to do that,
Right.
Some things changed. We used an extra level of indirection, and
No,
we maybe used a
but
larger-
I think the answer to that is that, again, I don't think we actually had to live through this problem. But the idea where you had to go and do some memory mapping thing where you said, okay, this segment is now data writable, and then you could like emit code
that
to
would-
it,
that would have
and
been
then
awful.
so you don't want to do that at a small grain size. You want to do it at the largest possible grain size.
Right.
And I'm pretty sure we had planned what the heck we were going to do if that happened. You remember there were these weird supercomputer manufacturers like Ardent and stuff like that. There were these guys who said, yeah, you have to design for our weird machines, and you could only do cache invalidations or executable and writable under very heavy trap to supervisor nonsense. Although, like I said, I remember we actually had to live through this, but we were living under the threat of having to do it. So we worried about this quite a lot.
Okay. I'm going to open the floor now. If anyone feels like the question hasn't been asked or answered, now's your chance. Remaining questions.
This isn't related.
Louder.
Oh, sorry. This isn't related to the paper, but I'm just curious because this paper was published like 20 years ago, and I feel like the field of CS was different back then. Because if you compare it to now, like I feel like when you think of the CS major, you think of like T-shirts, very chill, right? And back then everything was very professional, and now we have like and then we have like now we have like different types of people joining in CS, right? CS is becoming more mainstream about it. And I was wondering like what are your thoughts on that? Like do you feel like this is like great or like I don't know, like or,
I think she's under the impression that we were a lot more professional than we
It's not going to work in CS, right?
Yeah, absolutely.
Yeah.
Yeah. So yeah, I want you to take that. I want you to take it first. I really do, because I'm interested in what you're going to say.
So I'm sorry, I have a little bit of hearing loss. I'm not sure I heard every word of your question, but the
People were so straight, nowadays they're sort of open and more.
So what was the name of what was the title of Stephen Levy's really infamous article on PARC? Remember
No.
the Rolling was it the Rolling Stone article?
I don't remember.
So
But of course, there's what the doormat said, for example, right? John Markov's book, right? Who
no. So the short answer is that I think there was quite a spectrum then, and I think there's quite a spectrum now. Although I think the distribution along the spectrum has shifted a good deal. From my memory, 60s, 70s, 80s, the bulk of computer-related work, which I think then was probably classified really under engineering, the term computer science was relatively new, was in fact done by people wearing white shirts in big companies. Xerox PARC was a bit of a departure, perhaps. And
Silicon Valley more generally.
And Silicon Valley more generally. And there have been a lot of books and articles written on kind of the rise of the Silicon Valley culture. And I think it's fair to say that we were among the, kind of the early instances of it.
Right.
But
More bohemian than you think, basically.
oh yeah, a lot more bohemian than you think. I mean, if I think of the people who were around in the 70s and 80s, I mean, just sort of locally in the Valley, I mean, there was us, there was the Stanford AI Lab.
Exactly. Yeah.
Those were.
So you're wearing their T-shirts, basically. You're under a misapprehension for how you're thinking about T.J. Watson Labs, and you're thinking of the East Coast rather than the West Coast. So,
Yeah, and in fact, there was a considerable East Coast West Coast divide. On the East Coast, I guess the one really notable exception perhaps was the MIT AI Lab.
yes, that's very notable. Yes, that's right. They really lived on the.
And what?
They really. Well, Bell Labs people were kind of straight. I mean, a lot of them wore ties to work, right? There's a book I will recommend. I guess you haven't read it. John Marcos, What the Dormouse Said.
No,
Yeah,
really.
and basically claimed that the modern computer industry basically is straight outgrowth of the hippie movement. So I hear you that you think things have changed and things always change, but I think you may be imagining sort of that there was a different race of people back then who did things like that, and that they didn't smoke dope and have sex and whatever. And this is the attitude that children have about their parents, and I understand that.
So I really wanted to bring in my Xerox ID badge from 1970, which I'm pretty sure I still have. I just wasn't able to find it. I looked like Johannes Brahms. I had hair out to here. I had a beard down to there, and I looked.
And
I looked like I smoked a lot of dope.
Right. So this isn't to criticize your point. There's a lot of things have changed, but maybe not as much as you imagine.
Mario, do you have that video of somebody demonstrating either self or Smalltalk that we saw at the lab once?
I do, yes. I have a couple of videos. I don't know whether you're thinking about the self video with Dave Unger and Randy Smith, or Randy Smith's ARC video.
I think it was the self one.
Okay. I actually had that on my
It's
plan.
just a window into that.
Well, so that was already the 90s.
Exactly.
So,
But yeah, you could see like a ThingLab demo. I mean, there was
Yeah.
a lot of stuff that you could probably still see in video of people at Park. And mind you, it did annoy the guy. East Coast. Sure enough, Xerox was an East Coast company, and people would use the phrase Webster and stuff like that, right? They would talk about Xerox headquarters, and when the Xerox guys in their suits would come and visit Park, and they would see all these people dressed sort of not as differently as you might imagine to the way people dress today, and then remember beanbags, and so that's right, and they would be annoyed, but in fact it was the West Coast created the culture that you inhabit now.
The Hiltzik book, I think, speaks to this pretty well,
Yeah.
and talks about that East-West
Right.
divide
Right.
and some of the incidents that were spawned from it, which was quite memorable.
I really thank you for the question, though. That was good.
Other questions?
Let's bring it back to something more technical. Dang, yeah. So going back just to the memory usage aspects of this, I mean, you can show on really big commercial software the iCache becoming a real problem. Even like Linux, for instance, famously somebody decided to alias the inline keyword to not do anything, and then all of a sudden Linux ran faster because they were just inlining wherever they felt like it.
It was prefetch.
Was it?
Yeah, it was a prefetch loop, and they removed it and went faster.
Yeah. So I guess this is as much for anybody that knows modern jitting as well. Is this iCache usage really taken into consideration? Because when you're jitting, you can just, as you guys saw, you just blow up the size of the code. Is there a trade-off where how much, is it just that you take a cache, you pick a number, and you say, I'm only gonna have this volume of JIT code at any given time, or is it a more, wishy-washy sort of line where you decide how much you're gonna JIT before you start blowing up your iCache?
I'm going to start with the customary weasel words, which is that it depends on the workload. I haven't been doing work in this area for close to 30 years, and I think you should ask that question of somebody who has been, because it's a really good question. It's a good research question. I have no clue about the answer. The only place that I've ever encountered or even addressed this issue in my own code had nothing to do with code generation. It was when I was writing some graphics code for GhostScript, and the way in which it partitioned some loops working over bitmaps were optimized according to what it thought the size of the data cache was, and that's something that people do all over the place now in high performance programming, and I just have no clue as to what's happened in the last 20 plus years.
Yeah, I don't know either, but you have to be careful when you do an analysis, when you're trying to think about the problem. You shouldn't be comparing the space explosion that occurs from the intermediate representation to the native code representation, because you're comparing apples to oranges. One has nothing to do with the other. The intermediate code representation, if it was kept and interpreted, wouldn't be what was in the iCache at all, right? What would be in the iCache would be the interpreter, right? Which has whatever code path it has, and you might speculate that that's smaller than the dynamic code that you're generating, but you don't know that with respect to loops. It might very well be a lot larger, right? Namely that there's all this overhead stuff that we happily eliminated. Say, for example, dynamic method lookup with its little hash table routines and stuff like that. And if you've done these clever tricks and you're in an inner loop, you have a whole bunch of a very long, possibly, interpreter code path, which now is completely obviated, right? So I'm not saying that I've given you the answer. I'm just saying that be careful of where your analysis begins.
But so, for example, I might speculate that if there's a really large gap between the RAM and the cache, what you might find is that it shifts the balance between bytecode interpretation and code generation, so that it now becomes, because the hot paths for the bytecode interpreter are certainly going to fit in even the hot, the furthest in iCache. It may very well be that dynamically generating compiled code for anything other than the hottest methods is simply not worth it. It may just not be worth it. And again, it depends on workload. And there's lots of research papers waiting to be written if they haven't already.
All right. So looking at the future of computer architecture, this is more toward Allan. That there's going to be a reprogrammable fabric, a hardware fabric, like such as FPGAs. What techniques do you think that can be learned from the just-in-time compilation for software that could be used as, say, for hardware? One idea being that as I'm running software, I can then port it onto, say, an FPGA and run that bit more efficiently on an FPGA.
Right.
What techniques do you think might come out that are also applicable from your own work?
We just,
Go ahead.
before Alan starts, some of the versions of the Alto and the Dorado that we worked with actually had dynamically loadable microcode. And something that we speculated about but didn't go very far with because the microcode space was so small was the possibility of perhaps not compiling, but dynamically loading, hot code into the microcode store on the fly, and that was just a segue to whatever.
Yeah, well, I was basically going to say that I think that not so much our work, but the immediate successors to or the near-term success, basically custom compilation, namely that if you're, and there are people who are doing this work as well. You're making a very specific point when you're talking about FPGAs, and that I'm afraid I can't be certain what to say. But just generalizing from your point, namely where there's a lot of dynamism in the hardware that it's somehow reconfigurable and the software can get hooks into that. I think the stuff that I know about that I find very interesting, I just brought up at lunch today, was speed power trade-offs. And that's really quite common, namely, should you power up a couple more cores? Should you increase the clock rate on some of the cores, so on and so forth. I think this is interesting. And so, and not really our work so much, although our work pointed to that, the custom compilation work, where you look at dynamically what's really going on in the machine and use the knowledge of what the possibilities are in the architecture, and that's underused to date. I think there's some real prospects there, how that plays to FPGA, really special purpose hardware, but tunable hardware, which already exists out there. If you have a laptop nowadays, Intel has given you stuff where it really is multiple cores. You can power them up, power them down. You can change the clock rate on some of those cores. You can change the cache allocations. There's an amazing number of knobs that they give you. And I think speaking of lots of research papers, there's lots of research papers on generating code that decides how to twirl those knobs. So I hope that answered your question.
So I don't know if I missed this, but when you did the work this paper represents, how close did you get to the Dorado performance?
They keep asking us this question, don't they?
So my recollection is that when we got to HPS on the SPARC, that we were sort of in the Dorado class to within a factor of 2 in either direction.
I definitely remember people subjectively, by way of complimenting us, would say this is easily as snappy as a Dorado.
Right.
People would say that, whether it's true or not.
Right.
They're just showing
But
us
with respect to the implementation of the 68K, my recollection is that it was in the range of 1/5 to 1/8 of a Dorado.
Yeah.
So we didn't get very close.
Does anybody want to hazard a guess of how much a Dorado cost, internal cost for Xerox to build? I'll give you a hint if you know anything about hardware architecture of that era. It was built out of ECL SSI chips, in other words, individual chips, NAND gate chips, right? It was built from NAND gates.
I think you got 4 NAND gates on one chip.
What's that?
I think you got 4 NAND gates.
4 NAND gates on a chip, yes, exactly. They're on wire-wrapped boards. And a power supply with a blower, and it was a company disk drive that was so large that when you first went into PARC, you noticed that nobody actually wanted these personal machines in their office. And so what they did was they drilled holes in the wall, and they ran the display cables into your office, and the Dorados would be sitting outside the office making the hallways very noisy because of the fan noise. So anybody want to guess how much these machines cost? Internal transfer cost was in excess of $100,000 each. And the goal at PARC, as I recall, I wasn't an employee at PARC, wasn't the goal they were saying eventually they're going to give 1 Dorado to every researcher, was that the idea? Right, and so that would have been they never quite managed that, I don't believe. But,
No, but we had a lot of them.
Yeah, so 1/5 of the Dorado on a machine, I know how much it cost to build a Sun 1, because I bought the parts, and it cost about $1,500.
What was the clock rate?
The clock rate of the Dorado? That's a really good question, but I think I could
60
probably
megahertz.
guess. The clock rate of the Dorado, the microcode clock rate?
I think the clock rate was 16 megahertz. It was 60 nanosecond clock.
Yes.
Yeah, 60 nanosecond
Yes,
clock. That
that's
sounds right. Yeah.
Sorry.
Yeah.
Wrong percent.
It was it had the memory, it had God's own memory bandwidth for the machine of that era. It was had an amazing amount of memory bandwidth. It could do 4 things at a time and right? I mean, it could refresh the display, right? It was a cool machine.
It was.
It was a really cool machine. It had it was really an incredible accomplishment.
In terms of complexity, if you just measured number of gates that you needed to implement that, how did that compare to the 68,000?
Number of gates?
Yeah.
I think as a processor complexity, it probably was quite similar, but the difference is it was dynamically so it was much more expensive. It was built in ECL, right? So that's a physics argument right there, because you got a 16 megahertz, 20 odd megahertz clock versus a 10 odd megahertz clock. So in a very expensive technology versus a very cheap one, right? NMOS versus ECL. But they also spent a lot of money on memory, right? In fact, I would dare say that the majority of the money on the Dorado went into memory. So because there was the microcode memory, which clocked very fast. It clocked, right? It was made from static RAM, basically flip-flops, right? And clocked at 16 nanosecond RAM, right? And it had prefetch, and it had 4, banks of registers. I mean, there was just a tremendous amount of RAM. Sorry, very, very fast RAM in the machine. And it was like 256-bit wide. It was ridiculous, ridiculously over-memoried, right? I mean, they really should have put 4 processors on one memory bus, because that was really over-engineered.
So you made a point about generalized hardware winning over specialized hardware in this kind of scenario, but are there like tiny extensions you could make to general hardware to make this kind of runtime system work better? For example, say if you had like barrier support, for example, to replace the redirection table, for example, like the load value barrier.
Well,
He doesn't like things like generation packaging, so he wouldn't want to.
well, I'm not going to speak to things like a read and write barriers, because those are common on mass market processors today. I mean, I think even the Intel x86 architecture has those these days. The one attempt that we made at that was to add support for tagged integer arithmetic, which we talked the designers of the SPARC into putting in, and it probably wasn't a good idea.
They hit me for it. I know that for a fact.
Well, I think there's a lot of blame to go around in that particular
absolutely.
case, because who asked them to
Yeah.
decide that when the check fails to trap into
Right.
supervisor space?
No. There were versions of those instructions that did not trap. There were versions of those instructions
That could be tested.
that simply said overflow.
Right.
And so you could do the overflow and tag
The
check
overflow
with
and tag.
a single test, and it still wasn't worth it.
I was just thinking, you made the point of how compilation always wins on interpretation, but then the issue is that sometimes, so the tag check is like an example where with enough perspective you can get rid of all the tag checks. But then there's other things, like the checks that you have to do on the back, branches and things like that. Maybe, the garbage collector support, where it's kind of harder to use compilation and get rid of. So if there's support to facilitate this JIT compilation, that's like a constant overhead that is there. Now I know that people have been getting to reduce that overhead, but it's still a real overhead, and it's an opportunity to maybe speed things up.
I'm sorry. I guess I'm not. I'm not quite sure what you're referring to.
I'm just following up on Martin's question. Just wondering whether there are things that are less amenable to using compilation to remove that are part of your runtime.
So memory management is a really good example, because it's one that just keeps coming back over and over and over again. The tension between people who want the absolute maximum amount of performance and are willing to pay with the fragility and the unreliability of manual memory management to gain it, and the people who say, we can push the runtime overhead of fully safe memory management down pretty much as far as you want, and at the cost of some additional complexity and some perhaps additional static whatnot. We can even do that in environments that need relatively demanding real-time response. And I actually sort of dropped out of the field about 20 years ago. And so I don't know what the state of the art is in terms of, kind of what the minimum hardware support would be for scavenging that would buy you
that would buy you a reduction in things like barrier testing. And as I said, it's my impression that the Intel processors may even have something like that in them.
I don't get the impression it's really usable. in the
Maybe
direct-
not.
I mean, the operating system might get in your way too.
And yeah, well, there's always the operating system. So, but in general, if you step back far enough and you look at almost any source of overhead in the execution of a program, I'd say kind of as a broad statement, I don't see sources of overhead that can't be addressed by some combination of of floating operations out to a larger context and doing dynamic specialization based on actual data configuration. That if I was going to put my money somewhere, that's where I would put it. It doesn't mean that you can do that for everything, but I think we'd have to drill a little deeper into specific instances before I'd really be persuaded that there's some area where you can't do that.
Okay, well, one more follow-up question on that was like, these systems, like you spend a lot of time tuning the JIT compiler to make it run as fast as possible because that's an overhead. Take a pause when you do the translate. I know you said you did these very straightforward ones, but as you do more specialization, it takes more time. And so I'm wondering, did you measure the difference in speed of the C implementation with assembly? I'm sort of going towards well, maybe that's where actually hand writing the assembly might be worth. It's almost like writing hardware, but you want to write the little code to make the compiler run as fast as possible. How much overhead did you see from writing it?
We did see when you were switching tasks in some large. I mean, when you were switching tasks kind of at a large grain, so that all of a sudden your hot code paths, a lot of the hot code paths moved somewhere else. We did see there were human perceptible pauses, on the order of fractions of a second, while code was being generated for the new path. If we had been more concerned about that, what we would have done would be to schedule or interleave code generation with interpretation.
We used to talk about that, having a hybrid strategy where we use an interpreter until it was worthwhile. Especially when you talk about cold start, you'd imagine where there's some reason that it was important to do something really quick for specialized applications, maybe more real time or something like that, where you couldn't tolerate with cold start pauses. The same issue would come up with garbage collection pauses.
Right.
But it does occur to me, this is something I've observed more than once, is that that when I was using the system that we created all the way back then, under certain circumstances, I'm a really fast typist. I know you're a slightly faster typist than I am, at least you used to be.
I was.
But I was pretty damn fast. And in 1982, I could type faster sometimes when the PS system was in a bad mood. I could type faster than it could echo my characters on the screen. But you know what? On my Mac nowadays, which runs about 2.5 gigahertz and has code's all written in some weird dialect of C, the same thing happens. So, and the machine is sped up by a factor of 2,000 and so on and so forth. So apparently pauses are tolerable in interactive systems, and people keep on adding crap into these systems until people start noticing the pauses, and then they speed them up after that. So I think that's what we did. We just sped our system up until it stopped being so annoying, and that's probably what people are going to continue to do. And as the machines get faster and implementations get better, as Peter said, we'll tackle harder problems, always at the hairy edge where the pauses are just kind of getting annoying. So I really, in my career, I really haven't noticed a difference. Systems are always on the hairy edge of about to be annoying until they're actually annoying because something's broken. Right? I mean, they're actually annoying often enough, but I mean, they're on the hairy edge of being annoying because the system software is a little bit slow, right? And it's always been that way. It's been that way for 40 years, so I don't expect it's going to change in the future either. It has more to do with people than with technology.
Well, I mean, currently, I think the problem right now is with the JVM, at least, it's the startup times. You know, like if you, I know they work real hard on these VMs that are for like JavaScript, where they have really fast startup times, because like a lot of times you just execute the code once. With the Java VM, it's like incredibly slow to start up.
Yes, I've noticed.
Yeah.
Yeah, that's right. It's
Yeah.
true.
It's the same phenomenon. It's just there's a massive amount of code on that. If you look at, a long time ago, I actually looked at how many classes were loaded before Hello World started, before main got executed, and even then I think it was in a couple of hundred, with 500,000 bytecodes running before you even got to main. I'm sure it got much worse than that, and people just keep shoveling more stuff in. Right? As the speed goes up, well, we can squeeze more stuff in before people
Hire more physicists.
Yeah.
Okay, so continuing the question about user experience, I've noticed a trend from what I'm going to call the good old days, when you ran a Smalltalk image or a list image, to nowadays where everything runs on Unix and the user experience is actually much less integrated, much less unified than before. Do you think we'll ever get back to like an integrated development environment, renewing system, all that stuff?
No, because and it's not for a technical reason. Your opinion, I want to hear your answer
You go
too.
first. You're doing fine.
If you look at the way that software gets created these days, and you look at people's expectations of what a software application or software environment brings with it, the number of different players and the number of different sources that contribute to software, the total user experience of the software that you have in front of you on your screen, is so large and so dispersed and answering to so many different missions, so many different criteria, that it's a constant struggle to keep any standards alive and working and usable at all, let alone trying to create a fully integrated, create and maintain and develop a really fully integrated user experience environment. I could actually rant about this at considerable length because I am temperamentally a pessimist, but I think I won't.
Maybe you guys all know this paper, in which case I shouldn't waste my breath. But I'd say the single most important paper to read to understand there might be more profound ideas, but nobody's written them down. I'm about to talk about Dick Gabriel's Worse is Better. So do you all know that paper? Does everybody know the Dick Gabriel's paper, which is quite old, at least 20 years old, called Worse is Better? Do people know that? Oh, okay. Well, I think that's basically most of the answer. Namely, and Peter used to say this, you don't give yourself enough credit because you anticipated that paper, but you had a shorthand for saying that. You said first to fill an unoccupied niche. You used to say that all the time.
Yeah, but
right?
that wasn't even my idea.
No, I suppose not. I first heard it from you. So what happens is we get these agglomerations of systems, and it's not just in computer systems. I mean, the way we shift gears in a car and steering wheels and the layout of keyboards on it. I mean, basically what happens is the first system that's good enough for doing something complicated that has a network effect basically is going to be with humanity forever.
Well, as long as the problem that it's solving continues to be relevant.
Yeah, right. Well, apparently keyboards are still important, for example. Right. So what you have in real systems, whether they're automobiles or things that let you type papers or whatever it is some agglomeration of these kinds of solutions that got put together, and you don't get to change them piecemeal because you're locked into that, and you don't get to change it in an integrated way because the piecemeal solutions are adequate. So. No, and I don't want to make Park sound like Camelot. Oh, I did want to say this. So you may not know this, Mario, what this picture is of. Yeah, I know you see the castle. Can everybody see this?
I know what the caption inside says.
Oh, you do? Okay, so then it's important. So what you see here, and maybe that wasn't close enough, I hope I'm not carrying your cover too badly, there's a balloon taking off from a lofty castle that's on a mountainous pinnacle. And so the interesting thing about this is a elaboration of an earlier cover of Byte magazine. It's a zoom in on a particular feature, and that was called The Land of Programming Languages or something, right? And what it was trying to do, the landscape of programming languages. And it tried to show a continent where there was, the land of Fortran and the Isle of Snowball and, so on and so forth. There was a fanciful picture of lots of languages, but all of these languages were heavily populated and had their own rather large piece of turf. And in the corner, very, very small, there was a tall pinnacle of a mountaintop with very few people on it. And it had a fortress-like redoubt, a castle, right, that was clearly unreachable. It was in the clouds, and it was clearly unreachable by anyone else from these other places. And it was labeled Smalltalk. And that was the time saying that Smalltalk, the Greta Garbo of programming languages, right? Everybody, it wanted to be left alone. The only place you ever got to see it was at Xerox PARC, right? And so the interesting thing about this was that it was leaving the castle, right? So that was important. So the answer is, there had been some weird congruence of events, some weird thing where people had been kept in deliberate isolation, right? In some weird experiment where they wouldn't be contaminated by the rest of the world, by all practical considerations, and they built a system like this. But that really can't happen unless it's done by crazy, impractical people. And so, no, it's not very likely to happen again.
Okay. Yes.
So modern JITs are kind of viewed as a black box. You kind of put your code in it and it optimizes it hopefully fairly well. So with having written an early JIT, what do you think is kind of the right level of information return to the programmer? You had Smalltalk, which I'm assuming wasn't a language designed to be JITted in the first place, and you're doing this optimization on it, and now people are saying, oh, my code's faster, but they don't have feedback on it potentially, or they're doing something like looking at the stack, and are they being told, or how are they being told this is a really slow, terrible operation to do, don't do it, or so what's the right amount of information, or how should the JIT communicate back to the users this is where you should be doing, or how do you push that back into another language?
I mean, that isn't just an issue for JITs, that's an issue for every compiler.
Yeah,
right?
But I mean the JITs, I guess now they kind of do multiple optimizations over time, so it's even more.
JIT can do that too?
Yeah.
The whole question about, what you're asking actually is a large and interesting question, which is kind of the information feedback loop between programmers and implementation technology, and the two always are in a feedback loop. I don't know that I have that good an answer to the question, and here's the reason why. What executes faster and what executes slower is going to be affected pretty heavily by the specific implementation technology. So, for example, I'm going to take a really stupid example, but it'll exemplify the reason that I'm hesitating a little. If you have a compiler that does strength reduction in loops versus a compiler that doesn't, the compiler that doesn't is going to complain that you've got this multiplying inside the loop and that's really slowing things down. A compiler that does strength reduction may be able to remove that multiply and replace it by an add. So that's a really simple example. But I guess I'm a little wary of that kind of feedback coming out of the implementation technology. Now, this may just be because, you know, I haven't worked with state-of-the-art program development environments for a long time, and
Because every time you need one, you write your own, basically.
well, it's happened more than once. But I'm a terrific believer in dynamic profiling, and I've you know, I have to credit someone for that. Someone who was a manager of the computer science lab at Xerox PARC for a relatively brief period was Jerry Elkind. And he was a great believer in measurement. And he really changed my whole outlook about measurement as a way to understand what's going on in especially in more complex systems. And so, to my way of thinking, the most valuable kind of feedback that I could get from a programming system is feedback that will tell me things about the behavior of my program that are perhaps not tremendously tightly that are perhaps less tightly coupled to the implementation technology. But then there are things that are on the borderline. For example, my language of choice these days is JavaScript. I do all my desktop programming in JavaScript, and there are differences of opinion about whether this is a good idea or not. But you know, so one of the things that has gotten added to JavaScript is a getter and setter functions. So you can do something that looks like a reference to a property of an object, and it triggers a procedure. Now, that's a really powerful idea, and it makes expressing certain kinds of things a lot more convenient. But that's an example of something which, in almost any implementation, in almost any reasonably straightforward implementation that I can think of, is going to come with a pretty substantial execution cost. So something that I would, for example, want to know out of an implementation is, how much is this feature actually getting used in the code that I'm running? Now, I'm going to turn around and contradict my own argument by saying, well, I said a moment ago, and many other people here have said the same, which is that by doing dynamic profiling at runtime, but having that profiling be done by the implementation, it can see where these things are being used and where they're not, it can avoid the overhead of checking for them. So I know I'm talking around your point, and that's because I don't have a good answer to it. It's not something that I've ever missed, but maybe I don't know what I'm missing.
I have 4 aphorisms to give.
Go for it.
One of them is that, and this is going back in history, Allan said, Lisp programmers know the value of everything but the cost of nothing. And that was to your point about getters and setters, right? So you look at a piece of code and you think you understand it perfectly well. In the case, there's people know about Lisp, namely S expressions all have values, so the value of everything with the cost of nothing, namely that one given, token in Lisp might take no time at all to execute, or everything's a long time. So the value of it gets it to be there. Anyway, that was one of the aphorisms. The other one it's not an aphorism, it was a joke I read quite recently in the most recent Go release notes. And it really hit home because you may or may not remember that one of the last things I did with Parc was work with Frank and, ParcPlace, was work with Frank and David on making this heavily instrumented garbage collection system where you could change. We made, for the last generation of the Smalltalk system that I worked on, a very Baroque memory management system where everything was tunable and available to the programmer. So did you ever use any of this feature?
Yeah,
You weren't silly enough to.
we had knobs out the wazoo itself.
Oh,
I can
good.
only imagine that
Right,
there was a
no,
strong influence,
David,
not just
no, but
hundreds
no,
and
David,
hundreds and hundreds.
exactly. And so, and we're talking about the size of all all these spaces. There's
Yeah,
large
yeah,
space and,
yeah.
and new space and all these different kinds of spaces, and you can tune every one of these sizes and the ratios and how often you look at them and blah blah blah. Right? There are lots of knobs and dials, and they come with default values. But who knows? You might change it, and your program might speed up.
Yeah.
You might not have any of these dreadful pauses and so on. Right? So. The most recent, like Go 1.5 or whatever, said that as an advance, they say they've eliminated all the knobs in their garbage collector, and they say they know that they've damaged the prospects of the professional storage management knob twiddlers union, but they couldn't care less, is what they said. So the point is that you're now saying that, gee, I would like a lot more knobs, right? I mean, about the thing I'd like to be pointed out when, maybe of your own program, right? That you start having knobs, start moving code around and saying this is, but, probably I think the advantage of profiling is, since there's no substitute for thought, the really interesting thing about profiling is what it tries to do is it tries to eliminate the vast majority of your program for being worth paying attention to, right? Not that it tries to tell you what the answers are of where you're, what you should do to fix the problem, but basically saying this is what takes up most of the time. Because surely you shouldn't be wasting a lot of brain sweat on speeding up the parts of the program that don't take much time. But then the next thing where it says this is a part of the program which takes much time, and here's why, but I won't fix it for you. You go and fix it, but I know exactly what your problem is. So I think there's a gap. If the program knows, and that's the custom compilation part, if the implementation system knows what to fix, then it should fix it. And then beyond that, you need to know where you should be spending your brain power figuring out how to speed the program up. I think I only remember 2 of my 4 efforts. That's why I tried to cover up for that.
That's a great question. I think we'll be returning to this topic indirectly through the rest of the course as we get more and more sophisticated optimizations, and the combination of those optimizations sort of removes increasingly the predictability of the behavior of the program. So it's definitely a topic we'll look at. Any more questions? Nathan?
I'm going to try and redeem myself for spoiling that earlier conversation with a joke, which is, how do you piss off a computer scientist after a talk, or how do you confuse and befuddle somebody? That's to raise your hand and say, didn't Xerox PARC do this in the 70s? Because there's so much came out of there, and nobody can quite remember all of it. So the only option is to assume you befuddle them.
Well, you don't have to befuddle them because they can say, yeah, probably.
Yeah.
I thought the standard response to that was, didn't IBM do it in the 60s?
So the point of telling this joke is, like, this paper, for instance, very influential. I'm sure there's just a bajillion things that came out of Xerox PARC that were super influential. And yet, if you tell anybody on the street about Xerox, they're like, oh, don't they make, like, copiers or something? So, like, do you have any insights, so many years later about how an industrial research lab should work to bring value to a company while still having impact? What did the guys in suits, you pissed them off by wearing t-shirts, but did you piss them off by spending a lot of money and not actually making any money? Or was it sort of accepted?
The book actually talks about this.
The deal is a lightning book.
There have been a lot of books written about Xerox PARC, and no answer that I could give would be better than what Daniel Hiltzik and other people have written. The first one, I guess, was Fumbling the Future.
Fumbling the Future, that's right.
So Fumbling the Future is probably still worth reading. Dealers of Lightning is certainly worth reading.
Do you know I was at the National Computer Conference when the Xerox Star was released?
No.
For the initial show? It was really quite an amazing thing. Because no one had ever seen anything like it. This was, I guess it was 1982, wasn't it? When we just started? Maybe it was 83?
Somewhat.
Yeah, 82, I think. And I was in the audience, and they had, the National Computer Conference was, big conference, and they had, so you have to understand, nothing like that, unless you'd ever been to PARC, you'd never seen any of it. Bitmap displays, mice, networks, laser printing, right? Well, desktop metaphor, right? At the start, you could drag things and put it in a garbage pail and stuff like that, right? And so I was in that room, like it wasn't a room, but in the hall, I guess, right? And they were showing the start, and they had a laser printer, right? And they had a file server. I mean, this is 1982, for God's sake. Nobody even understood what these people were saying, right? The local area network and stuff like that. This guy with a microphone standing up doing this stuff. Now, I had known a little bit about this because I had just met Peter, and I knew this stuff, but it was amazing you could buy this stuff, right? And so, it really was interesting that Xerox actually did have this stuff. It was there. They were selling it. By the way, before I complete that story about standing there, I will say that later when I got back to the office, I said, I'll buy one. What the hell, right? And I called Xerox. And I basically said, I want to buy one. And their answer was, no. No, and they said, well, you said how many people were in your work group and stuff like that. Our system is only for work groups of 50 people and larger, and they had I didn't profile properly, and I just wanted to buy the machine I saw. They said no. So that might be one reason why they fell. But I want to finish that particular story. So I'm standing there, and this guy is waving his arm. He's dragging documents from a file. He opens this file. I mean, they still don't have this, actually. You remember you would drag a drawer open, and you would see files in a filing cabinet, and you'd open the file folder, and a piece of paper would come out, right? I mean, it was like anamorphic up the wazoo, right? You remember this? It was like
I've seen demos.
Yeah, it was just amazing. And they did this, and I'm just watching. I'm in complete awe, as is everyone else in the audience, right? And we're just hanging on this guy's every word. He's using words we don't understand. Local area network, file server, all this stuff, right? 1982. And I'm sitting there, but there's this guy standing next to me. And is profanity acceptable here? Because the guy's going, shit. And really loud. He said, fuck me. God damn it. Fuck. Shit! God fucking damn it! Shit! It's like, and this guy's there, and I'm really hanging on every one of his words, right? I'm really interested in this guy. And this asshole next to me, he's like standing there, and he's right in my ear, and he's going, fuck me! So, I'm going to turn to this guy and say, shut the hell up, it's Steve Jobs.
I think we should end on that. Thank you very much for coming.
I don't remember you telling that story.
Adele has her version of Steve Jobs seeing this stuff. But Steve Jobs also saw the stuff.
Yeah, exactly.
And this is while he was working on the research. He saw the stuff.
For the students, please don't leave yet. I have your guys. Well, okay, so we call it. I have your assignments here, so I can come up and come get them.
Wait,
Yeah.